Greetings to all the dignitaries. Myself, Ritinder Kaur. I'm a research scholar in School of Computer Applications at Manav Rachna International Institute of Research and Studies. I'm here to present my paper titled A Novel Boundary Adaptive Oversampling Approach for Intrusion Detection. This paper is presented for the journal Indonesian Journal of Electrical Engineering and Computer Science. Now, the swift progress in technology and the escalating dependence on network computer systems have resulted in a striking surge in cyber threats and intrusions. To counter these evolving attacks, intrusion detection systems play a crucial role in safeguarding the computer networks. However, the traditional IDS methods face challenges in detecting the novel and sophisticated attacks, particularly when dealing with imbalanced network traffic. Data imbalance is a prevalent and critical issue in intrusion detection, posing significant challenges for machine learning algorithms. As a result, the machine learning algorithms, they struggle to identify and predict the minority classes accurately, leading to a high false negative rate and decreased overall performance in detecting the intrusions. This issue is particularly problematic in real-world applications, where the minority class represent rare events such as network attacks or unauthorized access attempts. Imbalance learning in intrusion detection systems has emerged as a promising approach to address this issue by improving the detection rate of minority classes. When the data imbalance, it can be handled at the data level by manipulating the training data samples or modifying the learning algorithm itself. Data-driven approaches can be either oversampling or undersampling. Oversampling replicates or synthesizes the minority class instances to achieve a balanced dataset. For example, random oversampling, SMOTE, or ADASYN. Alternately, the undersampling reduces the majority class instances to achieve a balanced dataset. For example, random undersampling, atomic links. These techniques, though they are simple and is easy to implement, but they may lead to overfitting and redundancy if not applied judicially. Alternatively, we have algorithm-based techniques. They adjust the learning algorithm to make it more sensitive to minority class instances. For example, we have cost-sensitive learning, threshold moving, ensemble methods. All of these methods, they apply to any algorithm without data modification, but struggle with severe imbalance and high computational costs. Researchers also propose hybrid approaches like SMOTE Boost, Rust Boost, and SMOTE-ENN that combine both data-driven and algorithm-based approaches to leverage their respective advantages. Now, this study particularly, it focuses on decision-based SMOTE variants that use decision boundaries as a mean for oversampling. Otherwise, there are multiple variants available based upon the sample generation principle, such as borderline SMOTE, SMOTE Boost. They use decision boundary by generating more samples near the decision boundary. Density-based variants such as ADASYN, FW mode, GS mode, they use sample density and distribution to create new instances, but they may amplify noise in sparse data sets as well. Clustering-based variants such as K-mean, SMOTE, they create clusters of minority samples before generating the synthetic samples, but they struggle with complex boundaries. Similarly, deep learning, attention hybrid methods have also been utilized in SMOTE DL, SS mode, federal base mode, but all of these, they are either computationally intensive or they have some data harmonization issues. Now, the effectiveness of the decision-based SMOTE variants that we are using in this study, it relies on the quality of the underlying classifier and majorly on their ability to accurately capture the decision boundaries. Also, the synthetic samples that are generated near the decision boundary, these approaches might not effectively explore the full space of the minority class, possibly overlooking crucial patterns or variations within it. Now, understanding these limitations, the study proposed a new approach, PA SMOTE, the proximity adaptive synthetic minority oversampling technique. For this research, we have used two popular datasets, NSL-KDD and UNSW-NB 15. NSL-KDD has two minority class instance classes, U2R and R2L, and UNSW has also multiple classes which are rare, For the purpose of our study, we have used the wormed class along with the normal class. Now, this study proposed this method of SMOTE, and the entire experiment, it was conducted using Python programming in Google Colab IDE, which is a very popular platform. Both the datasets were initially optimized for the experiment. NSL-KDD containing 42 features and one class label. Out of these, 3 features, which were nominal in nature, were optimized and transformed to their numeric counterparts, and they were scaled using min-max normalization. Similar preprocessing was also performed on all the 49 features of UNSW-NB 15. After this, the rare classes were extracted from both the datasets to continue the experiment. Now, to balance the training dataset, the proposed SMOTE method is being displayed in the adjacent figure. It was applied on NSL-KDD and UNSW both. Now, the working of this proposed algorithm is that it initially extracts the minority class samples and the normal samples, and then it trains a classifier on the dataset to provide information about the decision boundaries and the distances. Then these the distances, they are used in the resampling process to generate the synthetic samples. In this experiment, we use decision trees to learn the decision boundary as they naturally segment the feature space during training and help in determining distances to these decision boundaries. Now, this information was then further used to generate more minority class samples. The distance from the boundary was calculated for each minority class sample, and they were sorted based on these distances. Based upon the range of distances, threshold values of 0.6, 0.4, and 0.2 were decided, and they were applied with the strategy to assign higher resampling rates to samples closer to the decision boundary than to the farther ones. While for generation of the synthetic samples, the interpolation method of cubic spline was implemented. After the resampling, the U2R class with a count of 11 was incremented to 842, and the R2L rare class with a count of 209 was incremented to 2603. Similarly, when the same was applied on UNSW, the minority class worm, which was initially at 130, was incremented to 6318. Now, the next step was feature selection. For that, the CFS-MHA technique, which is an ensemble of the correlation feature selection using meta-heuristic algorithms for searching the feature space, was used. The experimental study revealed that it is efficient in extracting most representative features from the high-dimensional intrusion detection datasets. And when it was applied to a resampled NSL-KDD dataset, it selected 15 features out of the 41. The modeling of this reduced NSL-KDD dataset was done by cost-sensitive adaptation of random forest. Random forest is an ensemble learning method prominently famous for its adaptability, robustness, and high predictive accuracy across various machine learning tasks. The same random forest algorithm was also used for model evaluation in UNSW-NB 15 as well. Now, in this study, we used 3 approaches. The first approach was using the initial training data set with the default parameters and imbalanced class distribution for all the 41 features. The second approach used feature selection on the imbalanced training data set and extracted the 10 most representative features after applying CFS-MHA. The third approach oversampled the training data set to balance it out using SMOTE, and then it applied CFS-MHA for feature selection and extracted 15 attributes, and then it generated the evaluation model. Results for all 3 are being displayed over here in the presented table. As it can be seen, approach 3 performed the best amongst the 3 in terms of overall accuracy of 78.76, and it increased the accuracy, precision, and recall for the U2R and R2R samples. Initially, without any imbalance learning and feature selection, the U2R samples had 0% accuracy, precision, and recall, whereas it was incremented to 42%, 53%, and 42% respectively. Again, for R2L samples, initially the accuracy was 0.001, which was incremented to 83% after applying the proposed PS mode. Now, the same approach was also compared to the state-of-the-art research works. The first thing that is evident is that still there is a lot of research ongoing in the field of imbalance learning on the employed dataset NSL-KDD. Also, it can be seen that some of the surveyed papers, they claim very high overall frequencies, but they achieve so only due to their biases toward the majority class. Even though some of them have recall rates, higher recall rates for U2R samples, but the precision rates are very low. PS mode with cost-sensitive learning outperforms all the contemporary approaches. Now, further tests were also conducted on UNSW-NB 15 with the extracted normal class and the rare class of worm. And 4 other oversamplers were also implemented on the dataset SMOTE, ADASYN, borderline SMOTE, and random oversampler to compare their performance. The base classifier used for training and evaluation was random forest classifier. As it is evident from the results, PS mode showed the highest precision of 0.82 and recall of 0.73 values, resulting in a balanced F1 score and a high AUC of 0.86, which is also evident in the ROC curve shown in the ADASYN graph. Now, to prove the statistical significance of PS mode against all the 4 oversamplers, the models were also compared using 3 statistical tests of pair t-test, Mann-Whitney U-test, Wilcoxon-signed ranking test. All the 3 statistical tests have been conducted to show the robustness of the proposed model. The null hypothesis for this test was to assume that there is no statistical significance between these models. And the p-value was taken, the significance value was taken at 0.05. Now, all the 3 tests, within all the 3 tests, the p-values, they were less than 0.05, which is the selected significance level. And thus the null hypothesis was rejected. The only exception was in the Mann-Whitney test between the proposed model and random oversampler, where the p-value was higher than 0.05, suggesting less statistical significance in these models over independent samples. Now, to finally conclude my work, this research endeavors to contribute to the advancement of intrusion detection systems by proposing an adaptive oversampling approach, aiming to elevate their accuracy, adaptability, and overall efficacy, strengthening the security of computer networks in the ever-growing landscape of cyber attacks. By integrating the decision boundaries and classification information into the sampling process, these variants present a promising avenue for addressing imbalanced data challenges and refining decision-making processes across diverse domains. The proposed approach demonstrated improvement in the performance of rare class detection by incorporating the concept of boundary proximity within oversampling. This adaptly captures the subtleties and complexities associated with minority classes, especially in proximity to the decision boundary. The experiment delved into optimizing hyperparameters by exploring different threshold values for the resampling process. This hybrid algorithm demonstrates adaptability as it dynamically adjusts and selects new instances for sampling after each oversampling iteration. Notably, it prioritizes generating synthetic samples in regions closer to the decision boundary, mitigating the risk of overgeneralization and enhancing the distinction between classes. Use of pruned decision trees for generating the boundaries gives an inherent advantage of early stopping, avoiding overfitting and underfitting. In contrast to SMOTE, the algorithm avoids the random selection of sample points from the feature space, reducing the likelihood of introducing noise into the selected samples. Now, although the algorithm performs satisfactorily, there is still scope for enhancement in correctly identifying these rare classes. Further tuning or different modeling approaches can be explored. Checking the extent of realistic data generated can be explored, and the same data sampling, imbalanced data sampling continues to evolve. Further research and development can be done in decision-based SMOTE variants. Also, by leveraging the tools and resources available for implementing these variants, practitioners can also harness the potential of decision-based SMOTE variants to elevate imbalanced data sampling and improve the performance of machine learning models across diverse applications. So the same study, it can not only be applied to intrusion detection systems, we can widen or broaden the implementation of this into different other domains such as credit card, fraud detection, or into medical imaging as well. So that will be all from my side. Thank you so much for being there and appreciating my work. Thank you so much.